Welcome back. So in the last class we have started our discussion on the AC to DC conversion stage. So where this AC to DC conversion stage would be present on the charger, it will be on the front end, that is out soon after your grid or the AC supply, which is generally used for our EV charging. Soon after that we will have an AC to DC conversion stage. So we have seen what are the converters which can be used. The first one was our diode bridge rectifier. So the issue with our diode bridge rectifier was, as we have an EV on the output stage, or we will be having a capacitor to maintain the DC link voltage. So due to that we had issue of spiky current, or the power factor of the current which was drawn from the supply was very less. Then we have seen our solutions, that was our boost PFC, where we had an power factor correction circuit. So the limitation of our boost PFC was, it had 3 devices in the conduction path for all modes of operation. So because of that the losses were higher. Then we have seen our bridgeless PFC, where we had 2 devices on the lower side of the bridge, okay, and we have eliminated the other devices which were used in our boost PFC. In boost PFC we had diode bridge rectified followed by an boost converter, whereas we have combined those two stages into a single converter and we have drawn this boost PFC converter. Okay, so how this was used? So we had operated the switch 1 and switch 2 at high frequency, such that the charging and discharging can be done with respect to the inductor. The advantage over here was the inductor was present on the AC side. So the size of the inductor will be very less compared to the solution where we had inductor on the DC side. Then here if you see, the diode was operated at high frequency. Okay. So how this diode is operated at high frequency, we will see that. We have also seen the duty ratio of the device, how they are calculated, and we have gone through the analysis for our boost PFC. The analysis can be repeated for these two converters, bridgeless and totem pole. The analysis will be more or less similar. So here, to address the issue of this bridgeless PFC, that the diode was operated at high frequency, we have shifted the position of our switching devices. They were connected in one leg and the diodes were connected in the other leg. We have derived our totem pole converter. In this we have seen the operating modes. So what is the advantage of this one? The main advantage is that one of the leg will be operated at line frequency, that is the diode leg will be operated at line frequency, and the leg which is containing the switches will be operated at high frequency. The switches are moved on one leg and the diodes are moved to the other leg, which will be operated at line frequency, whereas in our bridgeless PFC it was operated at switching frequency. Okay. Now in this case, what will be the functioning of this totem pole? So in the positive half cycle, when I want to charge the inductor, I will turn on S2. So if I apply cable in this loop, I will observe that the inductor is directly connected in parallel with the supply. So it will get charged, it will store some energy. After that, we will disconnect the pulse from the S2, or we will turn it off, and simultaneously we will give pulse to S1, or we will be turning it on. The current will be flowing through S1 and it will be completing the path S1 over here. So and in turn it transfers the inductor which had stored the energy in the first case. Now it will be discharging through the load and it will be transferring the power to the load end. Now during the negative half cycle, we will do the complementary operation, that is switch 1 will be used for energy storage and switch 2 will be used to discharge the inductor. Okay. So in this case we are using switch 1 whenever we want to charge it, we are using switch 2 whenever we want to discharge it. If I mark the current direction in both the half cycle, the inductor was carrying current in this way in the positive half cycle, in the negative half cycle it is carrying current in the opposite direction. That is what is the main advantage, because of which we get the smaller size of inductor in this type of converter. Then let us understand what was the issue with our bridgeless PFC, why we said that the diodes were operated at your high frequency. Okay, so let us consider only the positive half cycle for an example. So in the positive half cycle, what was the operation of our bridgeless PFC? The switch 1 was turned on and switch 2 was turned on to create an short circuit or to connect the inductor across the supply, so that it gets charged. Then when we wanted to discharge it, we were turning off the pulse from S1. Okay, the S1 was turned off and S2 was maintained with the pulse. Okay. So what was the advantage of this one? So if you see, we were going for the switch operation which was at high frequency, but we have not considered the operating frequency of the diode. Okay. If I see over here, it was not carrying any current when it was in the charging mode. When it goes into the discharging mode, it carries the current. So, now diode has to switch at the switching frequency. Why? It is turning on during the stage 2 or the discharging mode, it is off during the stage 1 or in the charging mode. So, your diode will be repeatedly making and breaking the circuit, or it will be switching at the switching frequency which is very high. Okay. Whereas, in this case, in the totem pole, what has happened? Now, we have just changed the position of our switching devices. The number device count are exactly same in these two converters if you compare. But what has happened in this case? If you see, in the positive half cycle, switch 2 was turned on, and simultaneously this D2 was also in the conduction. While discharging, I have turned on switch 1 and I have removed pulse from the switch 2, but if I see, the diode 2 is still in the conduction mode. Okay. So, for the entire positive half cycle, D2 will be continuously conducting, whereas D1 will be continuously off. So, if I see the frequency of operation of the diode in this case, for one half cycle D2 is on, for the next half cycle D1 will be on. So, they are operated at line frequency or the supply frequency, which will be 50 or 60 hertz, whereas in this case they are operated at high frequency, and the switching loss of the diodes will be higher compared to any of our switching device, that is IGBT or MOSFET. Because of that, this had suffered from higher switching loss in the circuit, or the efficiency of the circuit was less compared to the efficiency of your totem pole, because of the simple factor that the diodes are operated at line frequency in this case. The advantage of this one, the inductor size is small, similar to our Bridgeless PFC, because it is on the AC side. So, inductor will be better utilized over here. Conduction loss is less compared to your boost PFC, where we had 3 devices for each mode of operation. In this converter, we have only 2 devices in each mode of operation. So, the losses will be less. Current through the inductor is bidirectional, that is the reason why we have a smaller inductor over here. Diode operates at line frequency compared to your bridgeless. Totem pole has got this advantage that the diodes are operated at line frequency. So, the loss which will be occurring in the diodes are very much minimized in this case compared to the bridgeless circuit. Demerit, the duty ratio is variable. Again, when we go into the analysis, we will see that the duty ratio will be proportional to your supply voltage, which is an AC. So, it will also have an variable duty ratio. Okay. So, it is not suitable for your low power applications. Now, let us see some analysis of this totem pole converter. So, when the switch was on, when S1 is on, what is happening? For this, in the positive half cycle, we have turned on S2 to charge the inductor. Okay. So, for DT time or for the charging time, S2 is on. For the discharging time, S1 is on, and whenever S1 is on, what will be the voltage which will be applied across it? It is the difference between the input and output voltage, because we have an bridge operation over here. For the positive half and negative half, this terminal will be selectively connected to the upper pole or the lower pole, that is the positive pole or the negative pole, based on which half cycle we are seeing. So, the difference between the input and output voltage will be applied across this inductor when we are going in the discharging mode. When we are in the charging mode, it will be directly connected to the supply voltage. If I carry out the same analysis of volt second balance and carry out the integration for the half of the cycle, as we are having symmetrical waveform. So, I will see that the duty ratio will again now be proportional to 1 minus of the ratio of Vs by V naught, and we have also seen why the V naught should be higher, because in the mode 2 it has to discharge. My inductor, if it is required to operate in the steady state, it should experience 0 average voltage over the cycle. So, over here in the first operation, first mode 1 operation, it was charging across the Vh voltage. So, in mode 2 it should get discharged, for that our V0 should be higher. Then now let us see what will be the, this is our duty ratio which we have seen during our boost PFC also. Now, for the positive half cycle, what operation has been done? We were turning on the switch 2 for charging, and we were turning on the switch 1 for discharging. Okay. So, what will be the duty ratio of the switch 2 for the positive half cycle? It will be equal to dt directly, and 1 minus dt, that is the complementary pulse, will be given to my ds1. Okay. Whereas in the negative half cycle, the operation will be flipped. Now, ds1 will be operated with the charging time, and DS2 will be operated during the discharging time. So, it will be getting the pulse which is complementary of your DS1. Okay. So, in this case for the positive half cycle and for the negative half cycle, the operation of the switches will be changing as per the given relation. So, if I plot this waveform for the positive and negative half cycle, what will be my observation? The switch 1 pulse is shown over here. Okay. So, we have this 1 minus dt for the positive half cycle for switch 1. Okay. So, that is why if I calculate 1 minus the green waveform, I will get this waveform. Then in the second half or in the negative half cycle, it is given directly the duty ratio function. So, it will be as it is, and similarly for the positive half it will be again 1 minus d of t. Whereas in the switch 2, it has exactly complementary operation when compared to the switch 1. So, in the positive half cycle it gets directly the duty ratio, whereas in the negative half cycle it gets 1 minus the duty ratio. Okay. So, these are the pulses which will be given to switch 1 and switch 2 in this case. Now, there is another variant of totem pole where we use all active switches. Okay. So, if you see what is the difference between the circuit which we have seen in this slide and the next slide. So, here we had 2 diodes and 2 switching devices S1 and S2, may it be IGBT or MOSFET, whereas in this case we have replaced the 2 switches by 2 diodes by 2 switching components or 2 IGBTs or MOSFETs. Okay. So, why this replacement has been done? So, in this case if you see, although my diodes were operated at fundamental frequency or the line frequency, when I compare the loss which will be created by a diode and the loss which will be created by your MOSFET or IGBT, so diodes will be creating an higher amount of loss. To increase the efficiency of this circuit, this solution has been proposed where we have replaced the diodes D1 and D2 by 2 switching devices, that is S3 and S4. Okay. So, if I want to operate that in the totem pole mode, then I have to generate 2 more pulses because we have got 2 more switches over here, but we have already discussed that in totem pole operation the switch connected in this leg they will be operated at line frequency. So, this is the pulse for your switch 3 which is getting on for an entire half cycle, that is negative half cycle, whereas switch 4 is getting on for the entire positive half cycle. Okay. So, although we have replaced the diodes with your switching devices, we are not operating them at high frequency, whereas the switch 1 and 2 are operated at the high frequency. We have maintained the line frequency operation for S3 and S4 or the leg 2. So, here what is the conclusion from this? So, this is an high frequency operating leg, this is a low frequency operation leg. Although the inductor current is at high frequency or it is equal to the switching frequency because it is charging and discharging within a switching cycle. So, beside maintaining the smaller size of my inductor, I had reduced the switching operation in one leg. So, the switching loss will be very less when compared to the case where S3 and S4 are also operated at high frequency. So, the next solution for this one will be your active full bridge converter, where we will come back to this circuit again. There we will see that both of them will be operated at your switching frequency. So, we will see the advantage and limitations of the active front end converter in the next few slides. Okay. So, before going into our active front end converters or converters made with your fully controlled devices, we will see the 2 solutions which we have already discussed. This is the first solution, diode bridge rectifier followed by an boost PFC circuit. Then we can use any type of isolated DC-DC converter which we have seen already. So, this is your one of the charger layout where we have used our conventional diode bridge rectifier followed by a boost PFC. The other solution which we will be discussing now is your active front end converter connected to an isolated DC-DC converter. Okay. So, what will be the merits and demerits between these 2 circuits? Okay. So, if I see the number of switching devices, here we had only 1 switching device, whereas we have 4 switching devices over here. But what advantage we have got from shifting from the diode bridge rectifier followed by an boost PFC to this solution? Over here if you see, we had the power flow in unidirectional mode because the power cannot flow in this way, or if I want to support the grid by discharging my electric vehicle which is having some charge, suppose my electric vehicle is fully charged. Now, the grid is going through peak loading condition where we generally have shortage of our generation. So, in that case it is desired that my electric vehicle to support the grid. So, I want the power to flow back into the grid. So, it is called as your vehicle to grid operation. In the normal mode, the power transfers from the grid to vehicle, so it is called as grid to vehicle mode. Okay. So, here I can only charge the vehicle, but in this case I will not be able to discharge because of the diode bridge over here, or because of an unidirectional converter which is connected at the front end of the circuit. So, now instead of seeing the diode bridge, now we have replaced that with an active front end converter. Okay. So, now what advantage we can get? Now I can go for G to V or V to G as per my requirement, vehicle to grid or grid to vehicle. As per my requirement, I can just set the command to the controller, the power flow can be controlled, because this is a perfectly bidirectional converter, that is it can transfer power from the AC terminals to the DC side, or from the DC side the power can be removed into the AC side. How this is done, those things we will be seeing shortly. When we go into our closed loop operation, we will see how this power flow is maintained from the AC side to DC side, and what will be the changes such that the power flow can be controlled in our active front end converter. So, the advantage is pretty clear over here. This is an unidirectional solution, this is an bidirectional solution, where we can go for our modern modes of operation, that is supporting our grid from the charged vehicles. Now, let us see some basic modes of operation for this active front end converter. Okay. So, classically we did not had sufficient power distribution technology to operate the devices at very high frequency. We did not had IGBT. So, the classical mode of operation was limited to a square wave mode of operations. So, what is then square wave mode of operation? The output AC which will be generated from the given DC link will be having an square wave shape. Okay. So, what will be the merits and demerits of this one? We will see that. So, what will be the pulses for this converter? For S1 and S4, we will be treating them as an pair, and we will be treating the S2 and S3, the remaining two switches, as complementary pair. Okay. And the operation frequency as seen from the gate pulse, they will be at the line frequency 50 or 60 hertz. So, they will be turning on once for an cycle. Okay. In the entire fundamental cycle of your AC, your switches will be turning on and off once. Okay. So, this is also called as your fundamental frequency operation of your active front end converter. Okay. So, here in this case, what will be the output voltage which will be generated when I turn on S1 and S4? Suppose if S1 and S4 are on, so this point will be connected to the top bus, this point will be connected to the bottom bus. So, S1 and S4 are on. So, what will be the voltage across this one? If I consider this as my positive and negative terminal at the output side, so I will see that I will get an positive DC voltage. Okay. Whereas on the other half cycle, when I turn on this S2 and S3, I will see that it is getting connected to the negative side of our supply, negative terminal of our AC terminal is getting connected to the positive of the supply, and positive terminal is getting connected to the negative. So, the output voltage will now become opposite of the previous case when S1 and S4 were on. So, we will get an negative output voltage, and if I see the shape of output voltage which I have just generated now, it is equal to your square wave. Okay, so, we have generated a square wave at the output AC terminals. But what was our requirement? We generally want our output AC voltage to be perfectly sinusoidal. So, if I go for Fourier series expansion to calculate what type of harmonics will be present in this converter, I will see that it will have more amount of harmonics, because it starts from the lower order. Dominant harmonic will be at the lower end. Okay. So, what is the dominant harmonic? Dominant harmonic is the harmonic which is just to our requirement, or it is the next harmonic compared to our fundamental component. Fundamental component is our required frequency at the output. Other than that, whichever components are present, they are called as harmonics. Out of this all harmonics, whichever will be the having the least frequency, that is called as your dominant harmonic. Why it is called a dominant harmonic? Because it will have the most effect on our load, because most of our loads will be having inductive in nature, because we have induction machines generally. Suppose I assume 5 volts at 1 kilohertz, 5 volt has 250 hertz, fifth harmonic, and on the other side we have the 20th harmonic. Example, considering my source voltage to be 50 hertz, so this becomes the fifth harmonic, and this becomes the 20th harmonic. Okay. So, in this case, which will be affecting the load in an worst way? So, we will see that. So, when my frequency is less, what will happen if I have inductive load? I know the impedance offered by inductor is equal to 2 pi f into the L value. Okay. So, here in the first case, when I subject it to fifth harmonic, the impedance will be less compared to when I subject it to 28th harmonic. So, what will happen now? Although my voltage is fixed, but the current which will be drawn at 250 hertz will be higher than the current which will be drawn at 1 kilohertz. Why? Because the impedance which is offered by our load is proportional to the frequency, as it is on the higher end side. So, the current drawn will be less because impedance is higher, whereas when we apply low frequency, it will draw an high amount of current. So, that is why we call them as dominant harmonic, because they have the most effect on the load. So, somehow I am able to shift this dominant harmonic to higher end side. I will see that my load itself will be having sufficient capacity to oppose any harmonic current, or there will be no requirement of additional filter in the circuit. Okay. So, this is the basic principle why we wanted to shift our dominant harmonic to an higher end side. Whereas, in this case what has happened, I will get all type of odd harmonics. Why only odd harmonics? When I go to Fourier series expansion, I will see that it is having symmetrical shape. So, they will be the other components, the even components will be cancelling out. I will be left with all odd harmonics, and the dominant harmonic will be present at the lower end, that is we will be having third, fifth and seventh harmonics. Okay. So, in this circuit, as it is in single phase, so because of that the effect of these harmonics will be higher on the load, because they are located at the lower end. So, now what are the limitation of this one? Already we have seen this. It has high amount of harmonics because all the odd harmonics are present, and the dominant harmonic will be at the lower end side, or its frequency will be less. So, its effect will be very high on the load. So, it has high TSD. The other limitation is no regulation of output voltage. Why? Once my DC voltage is fixed at VDC, so what will be the voltage over here, neglecting the loss, onset loss of the devices. So, I will get the VDC. Whenever S1 and S4 is on, it will be connected to plus VDC, this amplitude will be equal to minus VDC when my complementary switches are on. So, now once the DC link voltage is fixed, suppose at 400, so my output voltage is also fixed. So, I do not have any option of regulating the output voltage or changing the output voltage. Okay. So, if I do not have this option, what will be the limitation? Now, we have already seen our application in electric vehicle. This battery voltage, if we are considering it to be the battery bank over here, so its voltage will be variable. So, I want, when I go for the charging operation, my AC grid voltage will be fixed. So, with a given AC voltage, I want that it can generate variable DC voltage, whereas other way around, if I am going for vehicle to the grid operation, my DC link voltage will be variable and I want fixed output AC voltage. So, because of that, I will be requiring regulation of the output voltage. Okay. So, what is the regulation? For a fixed input or output voltage, if I am able to change the other side of the voltage, I say that to be the converter to have an capacity to regulate. In this control technique, we do not have any option to change the output voltage. If my any one of this voltage get fixed, the other voltage ultimately gets fixed. So, we do not have any function of regulation in this case. Okay. So, this ratio between your input to output voltage is called as modulation index. We will see that in the next lecture, where we will be going for our closed loop operation. Then, what was the next solution which was proposed? So, instead of generating an square wave, can I generate an quasi-square wave? What is a quasi-square wave? It will have finite zero duration. Okay. So, what was the other issue with our previous method? We had complementary operation, that is whenever S1 was getting off, we were turning on S2. Okay. In the previous case, we did not had the advanced gate drivers. So, this was creating an issue of short circuit. What is in short circuit? If by mistake, if S1 or S2 turns on simultaneously, I will lose the control of the circuit, because we will have a dead short circuit over here, because the entire leg has been turned on, or the on state drop, if it is neglected compared to the DC supply voltage, we have a dead short circuit. So, we will have a huge amount of current and the circuit will be damaged. So, because of that, we had one more concept, that was your dead band. So, we have to introduce dead band between S1 and S2. In the olden days, this deadband requirement was very crucial because there was not sufficient technology to do that. Nowadays, we get advanced gate drivers which by default generate two complementary pulses which are small deadband, or we can do that by using our DSP code also. Okay. But olden days, this was a major issue with our complementary operation, and the other limitation was we got fixed output voltage. So, we have shifted from a square wave to a quasi square wave, where if you see the simultaneous operation is avoided. We had some zero duration during which the switch can be commutated or it can successfully turn off. Okay. The other advantage over here is by changing this width, I can change the output voltage now. So, I have got voltage regulation, or I can, if my DC link voltage is fixed, then the AC voltage can be changed. Okay. What will be the limitation of this one? Still the THD will be higher compared to our high frequency operation, because the dominant harmonic will still be at the lower end side. So, and we have seen that if the dominant harmonic at an lower end frequency, so it will have an major effect on the load. The advantage over here was regulated output voltage is obtained, still the harmonic is dominant harmonic at the lower end side. So, we will have still higher percentage of harmonic and its effect will be very high, as the load impedance will not be sufficiently high to oppose your low end harmonics. Okay, so that also we have discussed. Now, the next mode of operation is your multipulse operation. Okay, suppose I want to reduce the harmonic to some more value, or some percentage should be less if that is my requirement. So, I can increase the switching frequency of my device and I can generate multiple pulses. Okay, so here if you see till the previous case, in the previous case, here it was still operated at fundamental frequency. That is, if I see the gate pulses for S1 and S4, they will be turning on once for an fundamental cycle. Whereas in this case, if you see, obviously we are generating multiple pulses, it is higher than my fundamental frequency. Okay. So, obviously from the previous solution, my switching losses will be increasing, but what will be the advantages we will be getting now? Here we have multiple pulses whose width can be varied as per the requirement of output voltage. So, regulation of output voltage is possible. It has lower THD compared to your square wave or quasi square wave operation, because what is our ultimate aim? We wanted to generate an sine wave. Here if you see, the deviation between the sine wave and your generated output voltage is less compared to the previous solutions. Okay. The more is the shape going towards your sine wave, less will be the content of harmonics. Okay. So, if we go for Fourier series analysis also, we will get the same conclusion. So, this will be having lower harmonics compared to your square wave operation. Whereas, when I see the next mode of operation, that is high frequency mode of operation, which is called as Sine PWM, Sine Pulse with Modulation Technique, or we sometimes called as Sine Triangle Pulse with Modulation Technique, Sine Triangle PWM or Sine PWM. In that, would compared to those solutions where we will be operating at higher frequency, the percentage of THD will be high, as it will contain still the lower order harmonics. Okay. So, compared to this solution where we will have the dominant harmonic at an high end side, here they will be located at the lower end side, because we are not generating such high number of pulses per cycle compared to the sine PWM. Okay. When we go into sine PWM, you will appreciate that we will have much more number of pulses in each of your half cycle, whereas in this case we will be having very limited 3 pulse, 5 pulse, 7 pulse and so on. Okay. So, here what are the advantage we have got over here? The output voltage was regulated, the THD percentage is reduced compared to the previous solution. Still we did not go into the high frequency operation, because in the olden days we did not had devices which can operate at very high frequency. Now we have IGBTs and MOSFETs, they can pretty well operate with your sine PWM. Okay, so we will see the advantages of our sine PWM over here. Okay, so this is our first type of your sine pulse with modulation technique, or sometimes it is called as sine triangle, because we will have one modulating signal and one carrier wave. Okay. This modulation signal is nothing but your reference wave or the required output voltage. Okay. So, as we have already discussed that we want sine as the output voltage. So, this is my reference will have an sinusoidal shape, and there will be a carrier wave which will control or determine the switching frequency of my device. Okay. So, the moment I increase the carrier frequency, the switching frequency of my device will be increasing. Okay. So, how that is done? and how this is proportional, we will see that. So, in this case, what will be the operation of this converter? In this case, this is method is called as a bipolar modulation technique. Why it is bipolar modulation technique, we will see it shortly. So, here we have one reference signal and one carrier signal. How we control that? We output will be equal to VDC when my modulating signal, that is V sine or V reference, is greater than my triangular or the carrier signal. I will connect it to positive DC bus voltage. When the other way is true, that is my reference sine wave is less than the triangular wave, I will connect it to minus VDC. Okay. So, if this is VDC, that is what we have discussed now. My output voltage will be equal to plus VDC when this case is true. Suppose this I consider as case 1, where my V sine wave is greater than a triangular wave. So, how will impose plus VDC over here? I have to turn on S1 and S4. Okay. So, the same case is written over here. For case 1, when this V sine is greater than the triangular wave, I will turn on S1 and S4. When the complementary case is true, I will turn on here S2 and S3. So, here I am operating two devices as pairs, that is S1 and S4, and the other pair is S2 and S3. Okay. Whenever my S1 and S4 is on, I give the complementary pulse, that is S2 and S3 will be off. When S2 and S3 is on, the complementary condition will be true, that is S1 and S4 will be off. So, this is how when I decide, or how I decide, that is whenever my sine wave is greater than the triangular wave, I will turn on S1 and S4 to apply an positive voltage. When the vice versa condition is true, I will apply negative voltage. So, now let us see this example. In this case, if you see the triangle at this dot, the triangle has crossed the sine wave, or the triangle is having at any point of time, the triangle is having an higher amplitude compared to the reference signal or the sine signal. So, it is falling under the case of case 2 when my triangular signal is on. So, what I will be doing? I will be turning on S2 and S3. So, I will get an negative voltage. If you see, this is your minus VDC, this is your plus VDC and 0 in between. So, here we get the negative voltage, okay, because my triangle amplitude is higher. And how we generate this? These pulses are generally generated inside an DSP, which is an digital processor. Okay, so we will be collecting samples, and at each sample we will be seeing this which condition is satisfied. Based on that, we will be generating pulse 1 or pulse 2. Okay, or we will be turning on S1 or S4, or if the complementary condition is true for that particular sample, we will turn on S2 and S3. So, during the sample time, we will consider that the output voltage is constant, because the sampling frequency will be very high. So, that is how we convert our analog signal into the digital signals. Okay. So, now here why this is called as bipolar modulation technique. Okay. So, if I see during the positive half cycle also, I have generated negative voltage. Okay. So, how the voltage at the AC terminal is changing? It is shifting between plus VDC and minus VDC for both the half cycles. Okay. So, what will happen to the load which is connected over here? Suppose we have a load which is inductive in nature. Now, there will be a high amount of dV by dt across the inductor. Why? It is repeatedly switching between plus VDC and minus VDC. Although we are in the positive half cycle, still we will be generating negative voltage, and vice versa, when we are in the negative half cycle, still we are generating positive voltage. Okay. And how this output voltage will be regulated over here? Just by adjusting the triangle sine wave amplitude. Okay. So, I can change the output voltage just by changing the amplitude of the sine wave. Suppose I want to decrease the voltage, I will go for an sine wave or the reference wave whose amplitude will be less than the previous case. How to change the frequency? Just by changing the frequency of this reference wave. Okay. Whichever is the frequency of the reference wave, that will be generated over here. Okay. So, if I connect a small filter over here, I will see that this will be having the same frequency. Okay. So, it will be having a sine wave which will be exactly following the graph. Okay. So, just over here, if I draw this, this is our 0 crossing. So, our sine wave will complete one half over here and the other half. Okay. So, if I connect a small filter over here, I will see that it is generating an sine wave. Okay. So, why I said it will be requiring a small filter? Because when we go to Fourier series expansion of this one, we will see that the dominant harmonic will be located at an very high frequency. So, the filter size is proportional to the dominant harmonic frequency also, or the frequency for which it has designed, or for the frequency which it has to eliminate. If that is on the lower end side, the size will be bigger. If it is on the higher end side, the size will be smaller. And in this case, now let us see the other mode of operation. Okay, so in the bipolar mode, what we have seen, that during the positive half cycle as well as during the negative half cycle, we were generating the complementary voltage. The advantage wise, it has shifted the dominant harmonic to the higher end side, so it effect will be less. If I keep the carrier frequency at a sufficiently high frequency, the load itself can manage the harmonics and we will not require any additional filter also. That case is also possible. And over here the regulation is possible, the frequency of the output also can be changed. Why this frequency of the output change is required? When we go for grid connection operation, we assume the grid is at 50 Hz, but that is not always true. We can have slight variation in the frequency, that is generally it is limited within band of 0.5 Hz or 1 Hz as per the grid code. So, what is the meaning of that? It cannot be at 50 Hz, it can be at 499, it can be 49.99, or it can be at 50.001. So, in that case I have to change the frequency of the output also. So, both of them are possible in this bipolar modulation technique. Limitation wise, it has imposed high amount of dV by dt stress on the load, because during the positive and negative half cycle we are generating the complementary voltages. That is, during the positive half also we are generating minus VDC over here. Okay. Now, next mode of operation. So, in this case we will not consider the switch 1 and 4 as the pairs, but we will have two reference signals. Instead of one reference signal, we will have two reference signal, one reference for each of the legs. Okay. Here we will operate switch 1 and 2, that is the devices which is in the leg 1 as one pair, and we will operate the switch 3 and 4 as the other pair. Okay. So, I will compare this with the triangular signal based on the same analysis, that is, whenever my reference signal is greater than the triangular signal, I will turn on and switch which will apply positive voltage. So, in this case S1 has to be turned on if the condition is true for this leg, and if the comparison is true that V sin is greater than the reference triangular signal, the reference voltage is greater than the triangular signal, I will turn on S3. Okay. So, we will stop over here what we have discussed in this class. So, we have seen our totem pole PFC, bridgeless PFC, then we have seen our active front end converter and their basic modes of operation, then we have shifted into our Sine PWM mode of operation. The first PWM mode of operation was your bipolar. Now, we are discussing about our unipolar modulation technique. We will continue from this point in the next class. Thank you.